Hello everybody, good morning. Myself, Dr. Shubhankar Sen from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the second lecture of the sixth module of the 12-week SHAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall illustrate the solution of Poisson's equation of heat conduction in two dimensions using linear triangular elements. So, the numerical problem which we have already solved in the previous weeks using bilinear quadrilateral elements for Poisson's equation of heat conduction subject to essential boundary condition, we shall solve the same problem today by using linear triangular elements in two dimensions. The problem was already solved using bilinear quadrilateral elements. So, this is the domain, this is omega. Here, the governing equation is k del square t plus q equals to 0. This is the x-axis, this is the y-axis. At the top surface, the temperature is 0 degrees centigrade. At the right boundary, the temperature is 50 degrees centigrade. At the bottom boundary, the temperature is 250 degrees centigrade. And at the left boundary, the temperature is 150 degrees centigrade. So, prescribed EBC, K thermal conductivity equals to 1 watt per meter degree centigrade, and the rate of heat generation is 1 watt per meter cube. So this is a square domain with length 1.5 meter and height also same value of 1.5 meter. 1.5 meter. So first we discretize this computational domain. So we know that the element level matrix equation is KETE equals to FE. This is the element level matrix equation system. In the first step, we discretize the computational domain. So we have two internal horizontal lines and two internal vertical lines. Now we split each square into two triangular elements. So this is x-axis, this is y-axis. So this is delta x equals to 0.5 and this is delta y. Delta x equals to delta y equals to 0.5 meter. Our global nodes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. Our elements are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18. So our number of nodal points in the mesh, this is 16, and number of elements in the mesh, this is 18. So we have two types of triangular elements. Both are linear triangles with different orientations. So this is the one set of triangular element. This is element E. Local node numbering is 1, 2, 3, and the other one is oriented in this manner, the way we are showing. So 1, 2, and 3, these are the local node numbers. So in both cases, we are getting right angled triangles such that the right angles are positioned at nodes 2 and 3. So for our case, NEN equals to 3. Now we generate the IEN array. IEN AE equals to capital A. So here we have this E, here we have A. A is varying from 1 to 3. Our number of elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So here we make the boxes first for generation of the IEN array, which is compulsory for making the mesh. This is 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So for the first element, our global node numbers are 1, 2, and 6. For the second element, these are 1, 6, and 5. For the third element, we have 2, 3, and 7. For the fourth element, we have 2, 7, and 6. For the fifth element, we have 3, 4, and 8. 3, 4, and 8. For the sixth element, we have 3, 8, 7. 3, 8, 7. For the seventh element, we have 5, 6, 10. 5, 6, 10. For the eighth element, we have 5, 10, 9. For the ninth element, we have 6, 7, 11. For the 10th element, we have 6, 11, 10. 6, 11, 10. For the 11th element, we have 7, 8, 12. 7, 8, 12. For the 12th element, we have 7, 12, 11. 7, 12, 11. For the 13th element, we have 9, 10, 14. 9, 10, 14. For the 14th element, we have 9, 14, 13. For the 15th element, we have 10, 11, 15. For the 16th element, we have 10, 15, 14. For the 17th element, we have 11, 12, 16. 11, 12, 16. And for the last element in the mesh, that is the 18th element, it is 11, 16, 15. 11, 16, 15. So this completes the construction of the IEN array. To make the numbering clear, let us make it 10. Similarly, this is 11. We make the circle little bigger in size. Now we shall construct the ID array as well as the LM array. Now this is our domain. We are generating the grid lines here. So the squares we are splitting into two equal sized triangular elements. Now we are having EBC at all the boundaries. So we have 0 equation numbers for the boundary nodes. So equation numbers are 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is for ID and LM arrays. So here at this node, our global equation number is 1. Here we get global equation number 2. At the internal node we get global equation number 3, and finally for the last internal node our global equation number is 4. So our elements are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and here 18. So we generate the ID array as ID array A versus IDA. So our A is varying from 1 to 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So for boundary nodes our equation number is 0. So 1, 2, 3, 4, these equation numbers are all 0. Then we have 5, 6, 7, 8. So at 5 and 8 our equation numbers are 0. So at global node 6 we have the global equation number 1, and global node 7 we have the global equation number 2. Similarly we have 9, 10, 11, 12, these nodes in the third row. So for 9 and 12 our equation numbers are 0. So for the 10th node our global equation number is 3, and for the 11th node our global equation number is 4, and for the remaining nodes our equation numbers are all 0. So 0, 0, 0 and 0. So for ease of understanding we identify the global node numbers here once more. So we redraw this picture. Here we shall show the global node numbers. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. Here we generate the finite elements. So we can cross check that at global nodes 6 and 7 our equation number is 1 and 2. At global nodes 10 and 11 our equation numbers are 3 and 4. So it means that we have the degrees of freedom T1, T2, T3 and T4 at the internal nodes. So this is the location of T1, this is the location of T2. Here we denote the unknown temperature as T3, and for this last node we have T4. So for remaining nodes our solutions are already given. So here we have the 0 equation numbers. So this is capital A, these are the global equation numbers, capital P, and then here we have shown the unknowns. Illustration of unknowns. Now we can generate the LM array by using the mesh picture where we have shown the equation numbers at the global level. So out of total 16 nodes, 12 nodes belong to the essential boundary gamma g. Therefore, we have 4 unknown temperatures T1, T2, T3 and T4. Hence, the assembled matrix will be of size 4 by 4, or P and Q, both they vary from 1 to 4. So we can easily construct the LM array here. So LM array is constructed as LM AE equals to P. So here we get E is varying from 1 to 18, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. A is varying from 1, 2, 3. The IDOF per node is 1 because only one degree of freedom. A number of element equations, it is going from 1 to 3 per element. So here we make the boxes for generating the global equation numbers belonging to individual elements. This is for the third element, fourth element, fifth element, sixth element, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, and finally for the 18th element. Now, if we look at element 1, our equation numbers are 0, 0, 1. If we go to element 2, these are 0, 1, 0. If we go to element 3, these are 0, 0, 2. For element 4, these are 0, 2, 1. For the fifth element, these are all 0 valued. For the sixth element, this is 0, 0, 2. For the seventh element, we have 0, 1, 3. For the eighth element, we have 0, 3, 0. For the ninth element, we have 1, 2, 4. 1, 2, 4. For the 10th element, we have 1, 4, 3. 1, 4, 3. For the 11th element, we have 2, 0, 0. For the 12th element, we have 2, 0, 4. For the 13th element, our global equation numbers are 0, 3, 0. 0, 3, 0. For the 14th element, we have all numbers as 0, 0, 0. For the 15th element, we have 3, 4, 0. 3, 4, 0. For the 16th element, we have 3, 0, 0. 3, 0, 0. For the 17th element, we have 4, 0, 0. And for the 18th element, we have again 4, 0, and finally 0. So now we have constructed all the arrays required in the pre-processing step. Let us go to the processor step. So first we look into the element level matrices that we have already calculated in the first lecture of this week. So here we partition the squares in equal sized triangles. This picture is for the IEN array. Now the element level matrices are obtained as KE equals to K by 2AB B square minus B square 0 minus B square A square plus B square minus A square 0 minus A square A square. This matrix we get when the right angle is positioned corresponding to local node 2. So when our element is in this configuration, local nodes 1, 2 and 3. So right angle is subtended at local node 2 of the element. So here our mesh size is A and here it is B in the vertical direction. We have already defined that delta x equals to A and delta y equals to B. So for the present case, A equals to B equals to 0.5. Therefore, we get here k is also 1. So we have 1 by 2 a square minus a square 0 minus a square 2 a square minus a square 0 minus a square a square. So this element level matrix, it takes the form half minus half 0 minus half 1 minus half 0 minus half and half. So this is the element level matrix. So if we look into our element numbering, then we can see that the elements for which the right angle is subtended at local node 2, they are with odd numbers. So here we replot the mesh. Here we see that for elements of odd number 1, 3, 5, 7, 9, 11, 13, 15 and 17, we get the local node number 2 with right angle, and because of that this element level matrix is valid for the odd number of elements. This matrix is valid for odd numbered elements. Now let us consider even number elements for whom the right angle is subtended at local node 3. So this is case 1 and this is case 2, where the right angle is subtended at local node 3. So local node 1, 2 and 3. This is element E. So the base is delta x, that is equals to A, and height is delta y, that is equal to B. So for this case, KE equals to K by 2AB into a square 0 minus a square 0 b square minus b square minus a square minus b square a square plus b square. Now putting A equals to B, here we get as, in addition to k equals to 1, this is 1 by 2 a square 0 minus a square 0 a square minus a square minus a square minus a square 2 a square. So this matrix finally reduces to half 0 minus half 0 half minus half minus half minus half and 1. So these element level matrices are valid for elements with even numbering, i.e. for E equals to 2, 4, 6, 8, 10, 12, 14, 16 and finally 18. So this was valid for E equals to 1, 3, 5, 7, 9, 11, 13, 15 and 17. So now we have generated the element level matrix, and element level vector is given by the element level vector Fe is given by Fe equals to QAB by 6, 1, 1, 1. So our A and B both are equals to 0.5. So this we can write with Q equals to 1 as Fe equals to Q into A square by 6, 1, 1, 1 equals to A square by 6, 1, 1, 1 for Q equals to 1 watt per meter cube. Now we can perform the assembly. The global matrix equation is KT equals to F, where K is a 4 by 4 matrix and F is a 4 by 1 vector. So we can generate K here. This will be a 4 by 4 matrix. K equals to K11. So this K11, if we look into the mesh, we can generate. So let us make the mesh once more. So this is global equation number 1, global equation number 2, global equation number 3, global equation number 4. And we generate the elements here. Element 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and here we have 18. So if we go for K11, then this K11, this comes as K331 plus K222 plus K334, K334 plus K227, K227 plus K119, K119 plus K1110, K1110. So this is the first term of the assembled matrix. This is the K11 term. Next we have K12 term. So for K12 term, this will give us this K12 term. So here we have contribution from elements 4 and 9. So K12 equals to K324. So this is K324 3 to 4 plus K1 to 9, K1 to 9. Then we have K1 3. So 1 and 3 they belong to elements 7 and 10. So K1 3 equals to K237 K237 plus K1310. So K1310. Now if we go for K14, this 1 and 4 they belong to elements 9 and 10. So K14 equals to K139 K139 plus we have K1 to 10 K1 to 10. So we have constructed the first row of this global matrix. Then we go for the second row. This is K21. So K21 will be equal to K234 K234 plus K219 K219. So we have got the K21 term. Next we construct the K22 term. K22 equals to K333 K333 plus K224 plus K332 plus K119 plus K1111 plus K1112. So we have constructed the K22 term. Next we have K23 term. Now this global equation numbers 2 and 3 they do not belong to the same element, and because of that we can say that K23 it must be equal to 0. So K23 equals to 0. Then for the second row we have the last term as K24. Now these equations 2 and 4 they belong to elements 9 and 12. So K24 equals to K239 K239 plus K1312 K1312. Next we go to the third row K31 K31. This is K317 K317 plus K3110 10. Then we have K32. Again 3 and 2 they do not belong to the same elements, and because of that K32 must be 0. Then we move to the diagonal term K33. K33 equals to K337 K337 plus K228 K228 plus K3310 plus K2213 plus K1115 plus K1116 and K34. It is in the elements 10 and 15. So K34 it can be written as K3210 K3210 plus K1215 K1215. Now we are left with the last row of this matrix, the fourth row. So first term is K41. So K41 equals to K319 plus K2110 K2110, then K42. This will be contributed by elements 9 and 12. So K42 equals to K329 plus K3212 K3212. Now K43, this will be contributed by elements 10 and 15. So K43 equals to K2310 plus K2115 K2115. Now we are left with the K44 term. So 339 plus K2210 plus K3312 plus K2215 plus K1117, and finally we have K1118. So now we fill the data. So we already know the element level matrices from the previous page, that Ke equals to half minus half 0, half minus half 0, minus half 1 minus half, minus half 1 minus half, 0 minus half half, 0 minus half half. So this is for E equals to odd numbers 1, 3, 5, 7, 9, 11, 13, 15 and 17. Then for E equals to 2, 4, 6, 8, 10, 12, 14 and 16, our Ke is half 0 minus half, half 0 minus half, 0 half minus half, 0 half minus half, minus half minus half 1, minus half 1. So easily we can understand that the element level matrices that we have written here, they are linearly dependent, because when we calculate these matrices, we take the derivatives of shape functions that certainly lead to the linearly dependent matrices at the element level, and when we perform the assembly and when we implement the boundary condition, we get finally a linearly independent global matrix equation system. Now we can substitute these values. So K331, so 1 is for an odd number, K331 is half. Then we have K222, this is for an even number, K222 is also half. Then we have K334, K334 is 1. Then we have K227, K227 is also 1. Then we have K119, so 9 is an odd number, so K119 is half. And K1110, this is in even number set, this is also half. So if we add these numbers, we see that we get 4. So K11 equals to 4. Next we go for the second term, K12. K12 equals to K324. So 324 is minus half. Here we get minus half. K129, this is also minus half. This gives us minus 1. So K12 equals to minus 1. Now we come for K13. This is K237. K23 equals to minus half. So this is minus half, and K1310. 10 is also minus half. So this is eventually yielding minus 1. So K13 equals to minus 1. Now we are left with K14 in the first row. K139. This is K139 is 0. And K1210. K1210. This is also 0. So this gives us K14 as 0. Now we go to K21. Because of symmetry, we can simply predict that K21 must be equal to K12 equals to minus 1. Still, we make the calculation. K234. So K234 is minus half. So this is minus half. And K219. 219 is also minus half. So this is minus 1. Then we have K333. K333 is half. K224. This is also half. K332. This is 1. K119. This is half. K1111. This is also half. And then K1112. This is half. So this is K229 plus K1111 plus K1112. Now K229, this is 1. So this should be 1. And we finally get as K22 equals to 4, K23 equals to 0, and K24 equals to K239. Now K239, this comes here. 23 is minus half. So this is minus half. K1312. K1312 is minus half. So this is also minus 1. So K23 equals to minus 1. Then we can easily say that K31 will be equals to K13 equals to minus 1. This is K327. So K327, this is minus half, and K3110, this is also minus half. So we get it as minus 1. So K31 equals to minus 1. K32 we already got 0. Now we can predict that K33, it must be equal to 4 because of the pattern we are getting for K11 and K22. So K337 is half plus K228. K228 is also half. K3310, this is 1 plus K2213. K2213 is also 1. Then we have K1115. This is half, and K1116, this is also half. So summing all of them, we get 4 as expected. Now for K34, we have K3210. K32 equals to minus half. K1215, this is also minus half equals to minus 1. Now for the last row, first term, we get K319 plus K2110. This should be equals to 0 because K14 is also 0. So K319, this is 0. This is 31. And then K2110. 2110 is also 0. So it is 0 plus 0 equals to 0. And then we have the K42 term, K329. K329 is minus half, and K3212. 3212 is minus half. This gives us minus 1. Then we have the third term, K2310. K2310 is minus half. K2115, is also minus half. So this gives us minus 1. We are left with the last diagonal term k44, and we certainly expect that this must be equal to 4. So let us calculate it. K339, this is equals to half, plus K2210, this is also half, plus K3312, this is 1, plus K2215, this is 1, plus K1117, this is half, and the final term is K1118, this is also half. By adding all this, we get 4. So we have constructed the the global stiffness matrix. Here we have shown the assembled or the global matrix capital K. This is assembled 4 by 4 matrix. This matrix is symmetric. So if we look into K12 term, this is K324 plus K129. So we can certainly predict that the corresponding term K21, it should be K234 plus K219. Similarly, if we look into the term K13, this is K237 plus K1310. Therefore, K31, the corresponding symmetric term must be K327 plus K3110. So here is a small mistake in the term K42. So K24 is K239 plus K1312. So the K42 term should be K329 plus K3112. The assembled 4 by 4 global matrix K is expressed as K equals to, so we have for the first row 4 minus 1 minus 1 0, 4 minus 1 minus 1 0. For the second row we have minus 1 4 0 minus 1, minus 1 4 0 minus 1. For the third row we have minus 1 0 4 minus 1, minus 1 0 4 minus 1, and for the last row we have 0 minus 1 minus 1 4, 0 minus 1 minus 1 4. So this is the appearance of the assembled matrix by using linear triangular elements of two different orientations. If we look into the matrix, this matrix is symmetric, this matrix is banded also, and this matrix is also diagonally dominant. So this is having 5 diagonals. So now we have to construct the element level load vector. So for this purpose we make the mesh once more. So here we have the mesh picture. Here we have 2 vertical grid lines, 2 horizontal grid lines. So we construct the finite elements of triangular shape. So this is global equation number 1, global equation number 2, global equation number 3, and global equation number 4. Elements are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So our boundary conditions were 0 degree centigrade, 50 degree centigrade, 250 degree centigrade, and 150 degree centigrade. Already in the previous problems we have shown that for corner singularity we can take average of the EBC data. So here we can write the temperature as 25 degree centigrade. Here we can write it as 150 degree centigrade, as average of 250 and 50. Here we take 200 degrees centigrade as the average temperature, and at the top left corner we can take it as 75 degrees centigrade. So now we can construct the element level load vector contribution and boundary conditions to yield the final load vector. So the final load vector F, it has 4 components, F1, F2, F3 and F4. So this comes from F1, F2, F3, F4 from the source term plus F1, F2, F3 and F4 contributed by the essential boundary condition. So this is certainly a 4 by 1 vector. Now if we look into the element level contribution for the load vector, we already got Fe equals to a square by 6, 1, 1, 1. So our F1 source will be F31 plus F22 plus F34 plus F27 plus F19 plus F110. So all these are equals to a square by 6. So we have 6 contributions. So we can say that this is a square by 6 into 6 equals to a square. A is 0.5. So this is 0.5 whole square equals to 0.25. Now all these components F2, F3 and F4, they have from the source term similar contributions from the neighboring elements. It means that for each of these F2, F3 and F4, we get 6 contributions from containing 6 elements, and value of this contribution is same for every portion. And because of that, we can say that F2 equals to F3 equals to F4 equals to F1 source in regard to the source term. So F2, F3 and F4 in regard to source term share same value as that of F1 source. This gives us F source equals to F1, F2, F3, F4 source equals to 0.25 1 1 1 1. This is 4 by 1, where F1 source equals to F2 source equals to F3 source equals to F4 source equals to a square equals to 0.25. So this is source. So we can illustrate one case of implementation of the essential boundary condition. Let us consider the F1 EBC portion. So let us consider F1 EBC part. So F1 EBC equals to, here we see this global equation number 1, it is having elements 1, 2, 4 and 7 with boundary nodes, and because of that the EBC contribution for F1 will come from elements 1, 2, 4 and 7. E equals to 1, 4, 2 and 7 will contribute to EBC, since boundary nodes, relevant boundary nodes belong to these elements. So the first term will be minus K 311 T11 minus K 321 T21. So this is the contribution from element 1. So we write the equation at local node 3. So here I is 3. So we have taken I equals to 3 and B belongs to B, eta G. Here B are 1 and 2. So one is B1, other one is B2 and element is 1. So we have written K311 T11 minus K321 T21. Now we have to go to element 4. So here for element 4 our I is 3 and our B is 1. So it is K314 T14. So this is contribution from element 4. Next we have contribution from element 2. In this case our I is 2. So it is K212 T12 minus K232 T32. This is for E equals to 2 and our last contribution comes from E equals to 7. Here only one node lies on the essential boundary. Here I is 2 and B is 1. So it is minus K217 T17. This is contributed by E equals to 7. So we have got the expression for the contribution of the essential boundary condition. Now we can write it as K311 K311. This is for odd number element. K311. Here 31 is 0. So this is 0 into T11. This was 200 degrees centigrade, 200 minus K321. So 32 is minus half. So here we get minus half into T21. So T21 is 250. We get here 250. So we have calculated the contribution from element 1. Now we go to element 4. So here this is for even number element. So this is K314. K314 is minus half. So here we get minus half into T14. So T14 will be 250 degrees centigrade. The next part is minus K212 T12. K212, this is 0. So minus 0 into T12. T12 is 200 minus K232. K23 is minus half. So this is minus half into T32. So for element 2, the third node temperature is 150. 150. The last contribution is minus K217 T17 minus K217. 1 is minus half. So this is minus half into T17. T17 is 150 degrees centigrade. So we have put all the contributions here. We can perform the calculations. 0 into 200 is 0. Half into 250, this is 125. Then we have again half into 250. This is 125 minus 0. Then we have plus 75 Then we have again plus 75. So if we add them, here we find that this is 125 plus 125 plus 75 plus 75. So this is 250 and 150. This is 400 equals to 400. So this gives us F1 due to EBC equals to 400. Therefore, F1 equals to F1 EBC plus F1 source equals to 400 plus 0.25 equals to 400.25. Similarly, we can calculate F2, F3 and F4 EBC contributions. So similarly, we can calculate F2, F3 and F4 all EBC counterparts. So let us show the case of F2. For this purpose, we need to make the mesh once more. So here we have the mesh. So these are the elements. This is global equation number 1, 2, 3 and 4. Our elements are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18. So F2 EBC equals to minus the contributions will come from elements 3, 4, 6, 11 and 12. So let us first consider contribution from element 3. For element 3, our I is 3 and B is 1 and 2. So minus K 313 T13 minus K 323 T23. This is from E equals to 3 minus K 214 T14. This is from element 4 minus K 316 T16 minus K 326 T26. This is for element 6. Then we have element 11 minus K 1 to 11 T211 minus K 1311 T311. This is contribution from E equals to 11 and final contribution comes from element 12. So this is minus K 1 to 12 T212 minus K 1 to 12 T212. So this temperature is 250 degrees centigrade. This is 50 degrees centigrade. This is 0 degrees centigrade and this is 150 degrees centigrade. So corners are 75 degrees centigrade, 25 degrees centigrade. This is 150 degrees centigrade and this is 200 degrees centigrade. So we have the expressions for evaluating this F2 EBC contribution. So For F2 we have boundary contribution from E equals to 3, 4, 6, 11 and 12. Let us consider the contribution from E3. So K 3, 1, 3. So let us first write these matrices here. K 3, 1, 3, K 3, 1, 3, this is 0. So this gives us 0 into T1, 3. So T1 is 250 minus K 3, 2, 3. 3 to 3 is minus half. So this gives us minus half into 250 minus K 214. So 214 is 0. So this gives us minus 0 into T14 is 250 minus K 316. So K 316 is minus half into T16. T16 is 250 minus K 326. K 326 is also minus half. So minus half into T26. So T26 is 50 minus K 1 to 11. K 1 to 11 is minus half. So this is minus half into T to 11. So T to 11 is 50 minus K 1 3 11, T 3 11. K 1 3 11, this is 0 into T 3 11, this is 50 minus K 1 to 12, T 2 12. K 1 to 12, this is 1 2 is 0. So here it is 0 into T to 12. So T to 12 is also 50 degrees centigrade. So this gives us 0 plus 125 plus 0 plus 125 plus 25 plus 25 plus 0 plus 0. So this is 300. Therefore, F2 equals to F2 source plus F2 EBC equals to 0.25 plus 300. So this is 300.25. In the similar manner, we can calculate F3 EBC and F4 EBC. For example, F3 EBC, this will be contributed from elements 7, 8, 13, 15 and 16. So if we consider element 7, in this case I is 3 and B is 1. So minus K 317 T17, where E equals to 7, K 317 T17 minus K 218 T18 minus K 218 T18 minus K 238 T38. This is from E equals to 8 minus K, here I is 2, K 1113 T113 minus K 1313 T113. This is contribution from 13th element. And finally, last two elements. Suppose for element 15, I is 2 and B is 3. So minus K, I is 1. So K 1 3 15 T3 15 minus, this is for E equals to 15, minus K 1 2 16 T2 16 minus K 1 3 16 T3 16 E equals to 16. We can substitute the values. K 317 equals to 0. So it is 0 into T17. T17 is 150 minus K 218. So 218 is again 0. So this is 0 into T18 is also 150 minus K 238 T38. 23 is minus half. So this gives us minus half into T38. T38 is also 150 minus half into T113. This is also 150 degrees centigrade now, minus K2313 minus K2313 is minus half. So this is minus half into T313. T313, this is 0. Then we have K1315, T315. K13 is 0. So this is 0 into T315. T315 is itself 0. Then we have K1216, T216. K1216, this is also 0. So minus 0 into T216 is 0 minus K1316. K13 is minus half. This is minus half into T316. T316 is also 0. So here we are left with 0 minus 0 plus 75 plus 75 plus 0 minus 0 minus 0 minus 0. So this is 150. So we get E3 equals to E3 source plus E3 EBC equals to 0.25 plus 150 equals to 150.25. Similarly, we can calculate the F4 EBC term. So F4 EBC, this will be contributed by elements 12, 15, 17 and 18. Let us consider element 12. For this case, our I is 3. So minus K 3 to 12, T to 12. This is for E equals to 12 minus K 2 3 15 T3 15 minus K12 17 K12 17 T2 17 minus K13 17 T3 17. This is for E equals to 15, for E equals to 17 minus K 1 to 18 T3 18 T2 18 minus K 13 18 T3 18. This is for E equals to 18. So this we can calculate as K3 to 12. K3 to 12 is minus half. So this is minus half into T to 12. T to 12 is 50 degrees centigrade minus K 2315. K 2315 is minus half. It is minus half into T315. T315 is 0 minus K1217. K1217, this is minus half into T217. T217 is 25. 25 minus K1317. T317. K1317 is 0. So it is 0 into T317. So T317 is 25. Then we have contribution from the 18th element. We have minus K1218. K12 is 0. So this is 0 into T218. So T218 is 25 minus K1318. T318. K13 is minus half. This is minus half into T318 is 0. So this is actually 50. Here it is certainly F. So this gives us F4 EBC equals to, the first portion is 25 plus 0, 25 plus 0 plus 25 plus 0 plus 0 plus 0. It is 0 plus 0 plus 0. So this is 50. Therefore, F4 equals to F4 source plus F4 EBC equals to 0.25 plus 50 equals to 50.25. So now we have constructed the global matrix and global vector. So we can represent the global matrix equation system as the global matrix equation system is KT equals to F, or we have 4 minus 1 minus 1 0 minus 1 4 0 minus 1 minus 1 0 4 minus 1 0 minus 1 4 minus 1 into T1 T2 T3 T4. So this is 4 by 4 matrix equals to our load vector components we calculated as 400.25, 300.25, 150.25 and 50.25. 400.25, 300.25, 150.25 and 50.25. This is K, this is T and this is F. F solve for T equals to T1, T2, T3 and T4. The matrix K is symmetric, banded and diagonal dominant. So its bandwidth is 5 and half bandwidth equals to 3. The KE were linearly dependent, but K is linearly independent and hence non-singular and invertible. So we can use direct or iterative solvers and then we can find the temperatures for this problem. Here in the K matrix there is error in the last row. So this should be -1. Certainly this is not 4 and here it is 4. This is the assembled matrix. Since there were some corrections in the assembled matrix, we show the assembled matrix once more at the end of today's class here. So this is the 4 by 4 matrix and the local node numbering for two types of elements. We indicate it once more in this portion. So this is local node 1, local node 2, local node 3 for the odd number of orientation. For the even number elements, we have this orientation as 1, 2, 3. Both of these triangles are right angled triangles. We conclude today's class here. We have solved a 2D Poisson equation of heat conduction using linear triangular elements. The global matrix is symmetric and pentadiagonal. We have illustrated the implementation of essential boundary conditions in this regard. For today's class, I suggest the textbooks of Professor T.J.R. Hughes and Professor J.N. Reddy. Thank you very much for attending today's class.